Hello, my name is Sagnik Nayak and I'm a computer science major.
Hello, I'm Eli Perula and I'm a mechanical engineering major.
Hello, my name is Rashni Panwala and I'm a double major in biological engineering and political science.
Hey, how's it going? My name's Kobe Jima and my major is aerospace engineering.
And we are
Our
SERK. Hey Kobe, what's an automatic chicken coop though?
Alright, so for FEDD, our job was to design and build an automatic chicken coop door opener that lifts a door at least 12 inches above the ground. And credit was going to be awarded for people that managed to find intuitive and creative ways to have the door function, such as using a daylight sensor.
The requirements of the automatic chicken coop door included the following: being 10 by 12 in a rectangle form that must go up and down a minimum of 12 inches above the ground. The door must be made of materials that are appropriate for an actual chicken coop and must be outdoors. The machine should clearly have two states, open and close. The machine should also have a manual switch to open and close the door, such as a lever, a pulley, or a handle of some sort. In first developing our automatic chicken coop door, SERK began by asking ourselves some questions. Who is this for? Why do we pick this? And what issues do we see as most important to be resolved? Through research in the topics of chicken behaviors and habits, a farmer's needs and interpretations, past model of chicken coop doors, background on the stability and cost of potential door material, and basic automatic mechanisms, we learned the answers to those questions. After this, we started to throw out some of our first ideas, such as motors, a garage door system, more motors, and even more motors. After quick debate, we realized that all of us saw the most success if we designed a coop that used motors. After numerous attempts trying to come up with models with motors, we could just not agree on a viable idea. So one day, we were sitting together, analyzing our four main motor-based designs, and we thought to ourselves, what about water? Quickly, the team scrambled to design new blueprints relating to water-powered movements. We did more research on hydrology and then set up a new design. This design became the background of our final product, and we only did variations to it after building had begun when we saw serious problems. In our final day of testing, we got the product to work and we did a recording of the test, as seen here. How it works is when water is plugged in, water leaves the stationary bucket and goes into the movable bucket. As the water enters, the door can go upward. Water will continue to pump and excess water will overflow back into the stationary bucket, keeping the door arise. When the user unplugs the pump, water will slowly drain out of the movable bucket and the door will begin to fall. We were not sure if this design would work on FEDD Day, so we made sure to have a video ready. When it came to moving our large door to the presentation site, the tubing came apart and our design was almost compromised. Some of the other design challenges we faced during our designing were the following. The door would not stay standing alone. Thus, we built a back support. The door did not have enough weight to come back down once it was pulled up, even when all the water was out of the system. So, we added PVC piping at the bottom and filled it with hot glue until it would fall on its own without being pulled down. The door also got stuck in the slits on the sides, so we sanded down the inside so there was more space for movement. The movable buckets were not heavy enough to move the door itself, so we had to deal with this through multiple tests. We tried to add solid metal weights, a different style of draining, and even letting water overflow out of it. We finally saw that with a larger movable water bucket, the door could come down if it was completely filled with water. Overall, our door did not work on FEDD Day, but we would still be able to present a unique idea that took much more research and much more effort than our original motor-powered door would have taken.
When it was time to present our project, things didn't go as planned. We noticed that our door kept getting jammed in the frame meant to hold it, making it more difficult to lift the door. This was before the judges showed up to our table, so we had time to make a few last-minute adjustments. We sprayed WD-40 in the frame with the intent to make the transition from closed to open smoother. As the judges appeared at our table, we were unsure of how our project was fare, but remained hopeful that it would perform as intended. We had tested our project a few times beforehand to make sure that it worked, and this attempt was expected to be no different. The water pump was plugged in and water started filling our makeshift bucket as intended, but things went downhill from here. Our door got jammed in the frame as water kept filling the bucket, and the friction in the system was too great for the pulley to overcome. Our bucket overflowed and did not release the water back into the larger bucket at the bottom, instead spilling water everywhere. We unplugged the water pump and cleaned up, then explained to the judges what our intended idea was behind the project. We ended up placing third from last. On the bright side though, we weren't in last place.
Based on our performance at FEDD and the unreliable method for pulling the door up, there are many aspects of the chicken coop door which we would change and improve upon. One of these factors would be to use windshield wiper fluid as a liquid rather than using water. We would make this change because the wiper fluid is more dense than water, which would allow us to use a smaller container than the one used. Another improvement we would make is using a wooden box to support the water system. This would be done in order to prevent any damage to the water system either from chickens, weather, or any other external source. An addition we would make on the entire system is to connect a timer to the pump in order for the door to be opened and closed at certain times of days, based on the needs of farmers or whoever owns a chicken coop door. A major modification to the design we created would be to use a pressure pump in the water system in order for more control of the water so that it doesn't spill everywhere. One last improvement we would alter on our design is to add a secondary pump on the water system in order to empty the water bucket that keeps the door open and to have better control of when the door opens and closes. Given more time to design, build, and test our automatic chicken coop door, we would have made these changes in time rather than having to sprint at the last second to get it all done. However, we have learned for future projects that it is better to decide upon the design early and begin the process of perfecting the design rather than trying to improve the design before even beginning building.
Time management is key to a successful engineering project. Future engineers must make sure that they start with something simple and work their way through the process. They must allocate enough time for testing, because what we learned from our mistake is that if they have a design which is out of the ordinary, they must allocate enough time for testing and corrections at the last moment. They will incur certain complications through their design process, and they must research and understand the concept they're dealing with properly so that they can build efficiently and implement the design correctly and efficiently on time for the design day.